Welcome back to What Is, the show where we take the universe's most complex head scratchers and try and explain them before your coffee gets cold. Today we're talking about ghosts, not the kind that rattle chains in Victorian mansions or fail to text you back after the third date. We're talking about the subatomic kind. We're talking about the neutrino. Right now, as you sit there, whether you're on a bus, at your desk, or hiding in the bathroom to avoid your boss, about 65 billion neutrinos are streaming through every square centimeter of your body every single second. They are passing through your skin, your bones, the screen you're looking at, the entire planet Earth as if it wasn't even there. To a neutrino, you're essentially a vast, empty canyon. In fact, if you wanted to reliably stop a single neutrino, you need a literal light year of lead shielding. So what are these tiny invisible speedsters? Why do they exist? And why did they make some of the smartest people in history want to quit physics and become goat farmers? Let's dive in. To understand the neutrino, we have to go back to 1930. Physics was having a bit of a midlife crisis. Scientists were looking at something called beta decay. Basically, an atom's nucleus spits out an electron to become more stable. Sounds simple, right? Except for one massive, terrifying problem. Energy was disappearing. In physics, there's a golden rule: the conservation of energy. Energy can neither be created or destroyed. It just changes form. But in beta decay, the math wasn't adding up. It was like buying a pizza, taking out one slice, and finding the box half empty. The scientific community was panicking. Some, like Niels Bohr, even suggested that maybe, just maybe, laws like the conservation of energy didn't apply at the subatomic level, which is the physics equivalent to saying, maybe gravity just takes weekends off. Enter Wolfgang Pauli. Pauli was a brilliant physicist, but he was also a bit of a grumpy perfectionist. In a desperate attempt to save the laws of physics, he wrote a letter to a group of physicists at a conference at Tübingen. He didn't even go in person because he wanted to attend a ball in Zurich. Legend. In the letter, he proposed a desperate remedy. He suggested that there might be a new, natural particle, a particle so small, so light, and so shy that it carried away the missing energy without ever being seen. He hated this idea. He famously said, "I have done a terrible thing. I have postulated a particle that cannot be detected." Think about that. Pauli was so stressed about the math that he basically invented an invisible friend for the atom just to make the checkbook balance. A few years later, Enrico Fermi, the guy who built the first nuclear reactor, took Pauli's idea and gave it a name. Since the particle had no charge and almost no mass, he called it the neutrino, which is Italian for little neutral one. It sounds adorable, like a brand of olive oil or a very small Vespa. But naming a ghost is one thing, catching it is another. For 26 years, the neutrino remained a ghost. It lived only in the ink of notebooks, on chalkboards, and in the imaginations of theorists. Most people thought we'd never actually see one. But then came Project Poltergeist. No, I'm not making that up, that was the actual name. In the 1950s, physicists Clyde Cowan and Frederick Grimes realized that if you wanted to catch something that almost never interacts with anything, you need two things: a gigantic source of neutrinos and a massive detector. Their source? A nuclear reactor at the Savannah River plant. Their detector? A giant tank of water laced with cadmium. The logic was this: if you throw enough neutrinos at enough atoms, eventually, purely by the laws of probability, one of them has to crash into something. It's like throwing a tennis ball at a chain link fence. Usually it goes through, but if you throw a billion balls, one will eventually hit a wire. In 1956, they did it. They sent a telegram to Pauli which read, "We are happy to inform you that we have definitively detected neutrinos." Pauli's reply? Thanks for the news. Everything comes to him who knows how to wait. Which is a polite way of saying, I told you so, I wasn't crazy. But as it turns out, the universe wasn't done messing with us. Because once we found the neutrino, we realized it wasn't just one, there were three. Welcome to the world of flavors. In the standard model of physics, neutrinos come in three types: the electron neutrino, the muon neutrino, and the tau neutrino. They are like the Three Musketeers, except they don't like each other and they keep changing their costumes. And this leads us to one of the greatest mysteries in modern science, the Solar Neutrino Problem. By the 1960s, we knew the Sun was a massive neutrino factory. Every time a hydrogen atom fuses into helium in the Sun's core, the process that gives us light and heat, it spits out an electron neutrino. A physicist named Ray Davis decided to count them. He built a detector deep underground in a gold mine in South Dakota. He used 100,000 gallons of dry cleaning fluid. Why a gold mine? Because you have to get away from cosmic rays. The Earth's crust acts as a filter, stopping the noise so you can hear the whisper of the neutrinos. Ray Davis sat in that mine and waited. He expected a certain number of neutrinos based on our models of the Sun, but when he checked the results, he only found a third of what he expected. 2/3 of the neutrinos were missing. This was a disaster. Either our understanding of the Sun was completely wrong, meaning that the Sun could be turning off and we wouldn't know, or Ray Davis was bad at his job. Spoiler alert, he was not bad at his job. He eventually won the Nobel Prize. The answer was much weirder. It turns out that neutrinos are the ultimate shapeshifters. As they travel from the Sun to the Earth, they oscillate. An electron neutrino might decide mid-flight that it feels more like a muon neutrino. Then it might flip to a tau neutrino. Ray Davis's detector was only tuned to catch electron neutrinos. The other 2/3 were there the whole time. They had just changed their outfits and he hadn't recognized them. Now here's why this is a bombshell for physics. For a neutrino to change flavors, it must have mass. Before this, the standard model assumed neutrinos were massless, like photons. But you can't have a change in something that has no mass and travels at the speed of light, because for light speed particles, time effectively stands still. If you have no mass, you have no internal clock. If you have no clock, you can't decide to change into something else. So neutrinos have mass, but it's incredibly, ridiculously small. A neutrino is at least 1,000,000 times lighter than an electron. They are so light that we still haven't been able to measure their exact weight. We just know it's not zero. At this point you might be asking, okay Mr. What Is Narrator Person, why should I care about tiny, invisible, vibrating ghost particles that don't interact with me? And that's a fair question. First off, neutrinos are the ultimate messengers. Because they don't interact with matter, they can travel through things that stop light. Light from the center of the Sun takes about 100,000 years to bounce its way up to the surface before it can zoom to Earth. Neutrinos, they fly straight out. A neutrino reaching Earth right now tells us what's happening in the core of the Sun right now. They are also our early warning systems for supernovas. When a star collapses, it releases 99% of its energy in the form of neutrinos before the light even breaks out. If a nearby star goes kaboom, our neutrino detectors will see it hours before our telescopes do. It's a cosmic heads up. Secondly, neutrinos might be the reason we exist. Now stay with me here. During the Big Bang, there should have been equal amounts of matter and antimatter. And when matter and antimatter meet, they don't go out for drinks. They annihilate each other into pure energy. If it were a perfect 50-50 split, the universe should be nothing but empty light. No stars, no planets, no TikTok. But we are here. Something caused a tiny imbalance, a little bit more matter than antimatter. Physicists suspect that neutrinos, specifically a process called CP violation, might be the key as to why the universe preferred matter over nothingness. We might literally be the leftovers of a neutrino argument. So how do we study them today? We've moved past dry cleaning fluid. Now we use the Earth itself. In Antarctica, scientists built the IceCube Neutrino Observatory. They drilled 86 holes 2 kilometers deep into the ice and dropped in a string of light sensors. When a high-energy neutrino from deep space finally hits an atom in the Antarctic ice, it creates a flash of blue light called Cherenkov radiation. It's like a sonic boom, but for light. By tracking that flash, we can point back into the deep universe and say, hey, that neutrino came from a supermassive black hole 4 billion light years away. We also have Super-Kamiokande in Japan, a massive stainless steel tank buried under a mountain, filled with 50,000 tons of ultra-pure water and lined with golden sensors. It looks like a sci-fi cathedral. In those quiet, dark places, we're listening to the heartbeat of the universe. So what is a neutrino? It's a contradiction. It's the most common thing in the universe that's almost impossible to find. It's a particle that weighs almost nothing, but carries the secrets of the biggest stars. It's a tiny, vibrating ghost that confirms the laws of physics, and then immediately breaks them. The next time you're feeling small or insignificant, just remember, at any given second, the entire universe is pouring through you. You are a crossroads for the cosmos, a place where trillions of ancient, ghostly travelers pass on their way to the edge of space. Not bad for a Tuesday. Thanks for watching What Is. If you enjoy learning about the particles that are currently ghosting through your DNA, make sure to hit that like button. Do you have a question about the universe that's keeping you up at night? Let us know in the comments. We might just make a video about it. And if you want to keep exploring the what and the why of, well, everything, don't forget to subscribe and ring that bell. It's the only way to ensure our next video actually interacts with your feed. Until next time, stay curious and keep asking those what is questions.